And they'll be talking about our dual arm platform for the control of magnetically actuated soft robots. As I'm sure you know, when a lot of people hear the word robots, they think of these bulky devices like this one here, seen in orange, which are normally used in factories to perform these tasks repetitively and over. And these are good at doing tasks like this. However, they're limited in the amount of different shapes or tasks their end effector could do. And in robotics, we refer to this as a limited amount of degrees of freedom. And this is normally directly related to the number of joints on the robots. So these big robots normally have a limited number of joints. So what has been done in the field of robotics is to increase the number of joints within a robot to increase its number of degrees of freedom. And if you along the length of the robot, like in these devices shown here on the right, we approach what's known as an infinite amount of degrees of freedom. And this means that our robot could be controlled to take any shape or any shape that one would like to desire. So now we've moved on from discrete and rigid robots to more of a continuous shape where the whole shape could be controlled. It provides a great advantage to us, but we still have limitations when applying this in the field, the medical field. And one great disadvantage would be that although the robot now is continuous, it's still made out of a rigid material. So if this robot collides with some complex structure within the body, for example, in some intravascular structure, it could cause pain and potentially damage and discomfort to the patient. So the next was transforming from rigid to something soft. An example of this is using soft robots. And this is a soft robot which is made out of silicon. And the advantage that this gives that now it's soft, so it could conform to these nonlinear shapes within the body, for example, and limiting any damage caused. The robot shown here is pneumatically actuated, and this means it's controlled by passing air throughout its channels. So it's soft and continuous. But one disadvantage which still comes about from this type of robot is that it's still relatively big. So though it provides loads of advantages, especially in, for example, laparoscopic surgery, it can't be used in intravascular use because of its size. And this comes from the fact that its form of actuation, so the way we're controlling this robot, is directly tethered to the robot itself. There's been development on this would be using magnetically controlled soft robots. Here, a soft material such as silicon is doped with magnetic materials, which allows us to reduce its size once more and be able to navigate complex and smaller areas within the body. This photo here is taken by a lab in MIT, which they show magnetic soft robots could be used in the, for example, to navigate neurological pathways. Now we know the advantages of magnetic actuation, but what are the types of magnetic actuation currently available right now? A platform is using a lot of coils to control the magnetic field, and the main advantage of that is that the current passing through each coil is directly related to the magnetic field generated. And this makes control algorithms fairly simple to integrate and to develop. However, these systems are limited in terms of their workspace. What we mean by that is the area with which the magnetic field could be controlled reliably. So the area with which our magnetic robot could be controlled is normally quite small. This disadvantage has been worked on by using permanent magnets. Here, an external permanent magnet, which is labeled EPM for short in this image, is used to control our magnetic field and in turn our magnetic robots, which is termed IPM for internal permanent magnet, where internal normally means because it's inside the body, that's why internal. And this kind of cuts back on the drawbacks of the coil system as we have a larger workspace, so it could be used in the medical field easier. However, the degrees of freedom, so the amount we could control this magnetic robot, are generally less than that of the coil systems. While coils have been shown to have 8 magnetic degrees of freedom, single EPM systems so far have been proven to have about 5 degrees of freedom, which they could control. And a system which kind of finds a compromise between these two magnetic actuation systems is that of rotating permanent magnets. Permanent magnets are rotated around their own axis and around the workspace to generate time-varying fields. But once again, this still has a bit of the compromise and drawbacks of both systems. So its workspace is slightly larger than that of coils, but not as big as permanent magnet systems. And the degrees of freedom are once again a bit larger than that of single permanent systems, but not as much as that of coils. So what do we propose to control magnetic robots within the medical field especially? Well, we propose this dual external permanent system platform, or DEPM for short. Here we have two external permanent magnets whose poses are controlled by two separate 7 degrees of freedom robotic arms. And we're using robotic arms in our case. And this is an example of our workspace and our setup. We're in this image here in our workspace, we have a Tesla meter, but this could be replaced by any sort of magnetic robot one would like to control, be it soft or not soft. Now we've kind of introduced our system. And in the previous slides, I've been talking a lot about the degrees of freedom and magnetic degrees of freedom. But what exactly do I mean by this? So what I mean by magnetic degrees of freedom are which magnetic components can we control? The primary thing we'd like to control would be the magnetic fields. And this would be how the magnetic fields change in the X, Y, and Z components of our system. So how the magnetic field is controlled in our workspace. Another component which we'd like to control is the magnetic gradients. And what this basically means is how the magnetic field changes in each direction. So the change, for example, of the magnetic field along the X, Y, Z directions, and the same again for the magnetic fields in Y along the same directions. So previous work has shown that out of these magnetic gradients, 5 of the 8 could be controlled independently. So together with the fields and the gradients, we could have a maximum of 8 magnetic degrees of freedom which we could control. I might say, okay, why are we looking into this complex maths? What's the advantage of controlling fields and gradients? Why do we need to know about them? Well, having full control of the fields and gradients allows to control independently the forces and torques actuated on our magnetic robot in our workspace. And this is where its importance comes from. Now we have our system with which we want to control, and we know what we want to control it and why. But how do we do this? Well, we could start by looking at the dipole model shown here, where U is the permeability of free space, and R is the distance from our magnet to the point of interest, and M is the magnetic moment, or you could think of it as the orientation of our permanent magnets. And by solving this equation backwards, we could find the position and the orientation of our two robots, our two external permanent magnets, to control independently our magnetic fields and gradients within our workspace, allowing us to control 8 independent magnetic fields and gradients. Take a step back and compare once again the system I've just described to those which currently exist. And let's pay particular importance to the advantages and disadvantages in the medical setting. One advantage which we'd like for sure is, do any of these systems allow for the miniaturization of soft robots by allowing for magnetic actuation? And yes, all of these would, or both rotating permanent magnet system, coil-based systems, and the one I've just described, the DEPM system. The next advantage would be high degree of freedom control. And while coil-based systems and our system has been demonstrated to be able to do this, rotating permanent magnets so far have only demonstrated 6 degrees of freedom control within their workspace. Another advantage would be scalability. Can these systems be scaled upwards such that they could be easily used and integrated? Although coil-based systems show the potential to be able to do this, that increasing their size requires an increase in the coil size and the currents being pumped through their coils, which increases both the cost and extra hardware needed to keep the heat generated due to the current passing through the coils down, while our system does not fall back from this. The EPM system would like to be increased in its workspace. All one would need to do is change the magnets on the end effect of the robots and increase their size. So this is another advantage of our system compared to the ones currently presented. And lastly, which kind of comes off the point I just mentioned, another desirable fact would be low running costs. And once again, coil-based systems would need out-of-cooling devices to keep to keep the heat down, which would raise the cost of their system. But although our system might have a high initial cost, as you need to buy these 2 robots, its running costs are comparatively quite low. Once again, I believe that the system we've just proposed is ideal for use in medical settings. And to prove, in fact, the use of this system in the medical domain, we ran a few experiments where we performed a CT scan of a human lung and extracted the data of the bronchial tree. And add any more extra radiation to the patient, as this is already performed right now when regular bronchoscopy is done. And we extracted, sorry for that. And we extracted 3 pathways to navigate with using our platform and a magnetically controlled soft catheter. The pathways are shown here as A, B, and C. That on the right, the red thing is the magnetically controlled soft catheter. Then we inserted the soft catheter within the lungs and used a robot to help navigate it through the complex pathways within the lungs until we got to the area we previously picked. The top right or the top left as well, you could see an overlay from shape sensing data through a fiberbrad grating overlaid on the STL model of a lung, showing how we successfully navigated our tentacle to the area which we picked within this lung cadaver phantom. And that's a quick summary of our dual EPM system, the control of magnetically actuated soft continuum robots. I'd like to say thank you to our team and to the funding bodies which made this possible.